Hi everybody, I wanted to go through some selected questions from our little test review here about polar and vector. So again, I'm not going to do all of them, I'm just going to kind of pick maybe one or two from each major topic just to make sure that if you had questions you can kind of hear another explanation to it. So why don't we just hop right in. So for converting polar to rectangular coordinates, you do want to be aware of knowing the position of where this coordinate would exist. So at -3, 5 pi over 4, realistically that should be in this quadrant right here based on the angle. But since it's negative, it's actually going to send it through the pole and basically put it back in quadrant 1. Now, if you're familiar with your special right triangles, you may already be able to identify this as a 45, 45, 90 triangle with a radius of 3, and you can break it down that way. What might be helpful is our general forms. X equals r cosine theta, y equals r sine theta. So knowing the angle and knowing the radius is just as easy for us to plug in, knowing our special right triangles as well as our unit circle makes this a pretty direct evaluation problem. Both cosine and sine have the value of negative root 2 over 2 at the 5 pi over 4 angle, times the negative 3 gives me positive 3 root 2 over 2 for both my x's and my y coordinates. Now with a question like this, because it's an axis angle, it's much easier for us to visually examine this. Now you can use the formula still, but so a radius of 6, pivoting pi over 2. So really that's just the coordinate 0, -6. I went down to the y-axis at 6, so it's really straightforward in that regard. Now, when we have a rectangular coordinate, again, it's really helpful to sketch it out. 2 negative root 3, so 2 here, 2 root 3 along the bottom. If you recognize this, this is a 30, 60, 90 triangle, where the reference angle is 60 degrees. Now, you could use Pythagorean theorem to get the radius, but part of this is knowing the fact that this is a special right triangle. Please be very aware that if I was giving you a question like this in the non-calculator section, it has to be an angle you can identify. And the only angles we identify are the axis angles from the unit circle and our 30, 60, and 45 degrees in the unit circle. So it kind of has to be one of those. So with my reference angle, 60, that means the hypotenuse is 4, and 60 is the reference, but the actual angle in standard position is 300 degrees. I got to make it, add up to be 360. Doing the multiple representations, so let's just take maybe this middle one, for example, -3, 5 pi over 6. So remember that because the angle is positive, I basically am going to go on the third radius, so 1, 2, 3. I'm going to pivot to 5 pi over 6 right here. But since the negative radius, I got to shoot through the pole and go to the other side at 3. So that will plot this point right here, essentially plotting it at the point 3 and then positive 11 pi over 6, where everything is in terms of positive value. Now, just wanting to rewrite it, some people can kind of do this visually. There is some kind of generic nice formulas here. I think it's really helpful if you don't have it in terms of all positive values already to start there, because you can see this is a positive radius. I need an additional rotation, so I just have to add 2 pi again, which takes me up to, 23 pi over 6 when I do common denominators and everything like that. My next one, negative radius with an angle between 0 and 2 pi. Actually, I'm pretty sure that's the original point in question, so that's a nice break there. And then finally, a positive angle with an angle that's negative. So again, that's why it's kind of helpful to have this here as a reference, because I can just subtract 2 pi from my angle, and I get 3 and then negative pi over 6. So if you don't already have it, if it's not given as a positive radius angle, it's really helpful just to start there. And manipulating that's a lot easier than keeping things negative. Okay, so changing equations. Now, I think for the most part, just kind of remembering that anytime you see x or y, you want to replace it with cosine and sine versions. So this would be 5r cosine theta minus r sine theta. equals 7. There's really not a lot to do here. You just want to get r by itself, and since I can just factor out the r from the equation, I can just divide, and that's it. That's all we really got there, not much else. Now, if I look at 10 real quick, x squared plus 1, y squared, this one is a little bit more annoying, but by distributing out this first term and doing a little bit of regrouping, we do get an advantage here. So, first thing, let's take care of the fact that there's a 1 on each side, so that will just make this whole thing equal to 0. This is r squared, so we can actually replace both x squared and y squared simultaneously using, essentially our Pythagorean theorem definition, x, y, and r. And x, like I said previously, is cosine equation coordinates. So by factoring out an r, we get these two results. R equals 0, which is just the pole, so there really isn't much to that. So we're going to focus our attention more here. R plus 2 cosine theta equals 0, and when I subtract negative cosine 2 theta, negative 2 cosine theta, that's our equation. Thinking about the way that would graph, it would graph in the negative x-axis out a radius of 2. Thinking about how circles work, that means the center would be at 1, 0, or negative 1, 0, sorry, and the radius would be 1, which is actually exactly what this equation was telling us from the beginning. So these two things are heavily related in how they are described. Now, going from back and forth, now number 12 is kind of a tricky one, because for a while I had given you this equation when you're trying to find the angle. So we can actually use that. We can use tangent freely like this, and so I get this. Tan inverse of y over x equals pi over 3. So to basically break out the tan on both sides will give us the ability to isolate x and y. Now the other benefit is tan of pi over 3 is a value on our unit circle, which would just be root 3. And then we can multiply both sides by x, and that's the equation going through that angle. So if you actually plot this in Desmos, for example, you'll just get a line with a slope of root 3, which is kind of how the tangent lines get the notation of touching a circle once at a point and going on forever, kind of bring it back to a geometry sense. Tangent itself is its own equation in polar coordinates too, interestingly enough. And then something a little bit more standard, something like r equals negative 3 cosecant. If I multiply both by sine, cosecant and sine are reciprocal, so they reduce to 1. So I get r sine theta equals negative 3. And sine, r sine theta, is just a y coordinate. So that's really all you need to be able to do for that. Now for graphing polar equations, there are some, keys to being able to do this. We've talked a few times about identifying the different shape types. So since this is just standard sine and cosine, this is just a circle, and just knowing which axis it goes down. So we've talked before about how this is the positive cosine axis, negative cosine axis, positive sine axis, negative sine axis. And you can certainly plot in some points and see what points I have in my answer key. So I'm going to fill them in, like the important points right here that feel useful to actually plot for you. And sometimes it's hard to see it with these points. So when we start plotting it, we end up seeing that we're going between 0 and 4. I think that's 4. Yeah, looks like 4. And then 2 is like somewhere out here. So we just really end up with a circle that has a diameter of 4 down the negative sine axis. So there's not really a lot to get point-wise for this. It's just identifying the shape for each kind. Speaking of which, we have a pedal curve. And a quick recap of the pedal curve. is that this is my maximum value. And depending on the number that's in theta, that tells me how many petals there are. Since this is an odd number, I get exactly the number of petals. Remember, if it's even, you get twice the number of petals. So sine's maximum normally occurs at 90, but since I'm splitting it into 3, my first maximum petal will occur at the 30-degree angle, and then following petals will occur symmetrically. Now remember, a circle has 360 degrees, but we've got 3 petals. So that means the first maximum will occur at the 30-degree angle. Then if I travel 120 degrees more, that's my next maximum. And then another 120 degrees more, my final maximum. And it should be a 120-degree rotation back. So since each one has a maximum value of 2, and make sure I line these up correctly, we get these, and then we just have to sketch our sort of flower petal curve. Okay, so that's really all you need for these. Getting coordinate points for these are really tough because they are kind of random. These all happen to be on nice symmetric points along the axes, so you would actually find them within plugging in. But if something had like 5 petals, 72 degrees is not something we know the unit circle value for, so a little bit tougher. So finding the vectors from 2 coordinate points, the key here, remember it's always x2 minus x1 for I, and y2 minus y1 for j. It's not interchangeable. It has to be, this is x1, this is y1, this is x2, this is y2. So it has to be negative 5 minus 6i plus negative 4 minus 4j. So negative 11i minus 8j. That is the direct vector. If you do it the other direction with x1 and y1 first, you actually get going from the ending point back to the beginning point. So you want to make sure you're subtracting P1 from P2. And then for these, you know, it's really just combining like terms. So u plus v, vector, add the I components. So negative 7, negative 5, negative 12i. Add the j components, negative 3, positive 7, minus 4. Same thing with subtraction, you just subtract the components. Actually, that should be positive 4, sorry. Scalars, just multiply like distributing. Again, nice and easy. So 8 times 3, 24i. 2 times 3, 6j. Done. So now our dot products will be all about doing sort of our one operation this requires, because we don't have standard multiplication. Remember, dot products are take the components, the i's, and multiply them. So 4 times 14, that would be 160. Plus negative 8 times negative 13, that's 104. I'm sorry, it's not 160. It is 56. And when I add them, I get 160. I looked at the wrong number, sorry. So again, your component multiplication is not like individually multiply them and that's it. It's multiply the i's, the j's, then add them. So it condenses into one number first. For your unit vector, which we normally denote as v hat, you first need to find its magnitude. Now remember, magnitude is its length, so more often than not use Pythagorean theorem. But for this first one, it's really easy because it's 2 squared plus 0 squared technically equals the square root of 4, which is 2. So the unit vector is the vector divided by its magnitude. So 2i divided by 2 is just 1i. In number 26, the magnitude is 13. So to get the unit vector, you do v divided by the magnitude of itself. So you get 5 divided by 13, which can't be reduced, plus 12 divided by 13, also can't be reduced, and that is the unit vector. So if it reduces, that's wonderful, but if not, you don't need to worry about it. And then finding vectors. So the components are pretty similar to polars in that it's magnitude times cosine theta for the I component, and magnitude times sine theta. So it's for the vertical. So it's pretty much the same, except the only difference is radius has been swapped with magnitude, which if you think about, the shape of these things, it's kind of the same. So this becomes 10 cosine of 120 degrees I plus 10 sine of 120 degrees J. And just using our unit circle knowledge, that's 5I plus 5 root 3J. One warning though, these were given in terms of an angle. If it's in bearings, and we've mentioned this before, that means that your cosine and your sine values flip-flop because your standard angle comes from our standard axis, but our bearing angle comes from the y-axis. So if this was a bearing question, we wouldn't be doing magnitude cosine theta I, we would do magnitude sine theta I if it was the bearing angle, and flip-flop it here. Now you could easily convert it. That would work too, but just be aware that when we give you bearing, it's vertical. So cosine and sine switch really definition in a sense. Determine if the vectors are orthogonal. Well, this one's actually pretty easy because you can see right now, just right off the bat, if I double it, I get the same vector, which means these are parallel. So remember, the whole purpose is if it's orthogonal, they form a 90 degree, that would mean its dot product should be 0. So if the dot product is 0, then they're orthogonal. Find the angle. So we have a formula here, V dot W equals magnitude of V, magnitude of W, cosine theta. So I already worked out all these things. The dot product was -2. Magnitude of V is 5. Magnitude of W is root 5. Cosine theta. So to get the angle, you just do -2 divided by 5 root 5. And then you just do cosine inverse of that. Now, this question is not asking for any specific form of an answer, no specific angle, no specific bearing. So whatever your angle is would be a good answer. You could give it as the negative angle value, or if you wanted to convert it to polar and vector components, you could, but that's how you would find that. I happen to not have that directly in front of me though. And then for this equation where it's the work equation, so we had this formula, work equals force times displacement times cosine of theta. So just looking at the question, using a rope that makes an angle of 25 degrees. Okay, well, there's theta. So we would put that as our cosine. It takes a net force of 450 newtons. Okay, there's my force. At a constant speed with a displacement, I know it says speed here, but it's saying the speed is constant and moves it 66 meters. So that's my displacement. So just plugging all that into a calculator, I end up with 26,917.3 joules. So that's really it. Just knowing where these components fit in. Now you may have noticed I skipped the page with the big polar graphs there. For those types of graphs, I really just wanted you to plug them in and double check what they look like and see. I would not ask you to sketch that manually without the use of a calculator. So those graphs are extremely complex. So I don't want you to worry about them. They're just kind of more things for you to see how they work with. So I'm going to skip 3 because basically 4 and 5 are asking the same questions. 3, 4, and 5 all about breaking down a component, but 4 or 5 are a little bit more challenging. So let's look at that. I have a box that has 2 forces being acted on it, both in bearings. The first one is north 45 degrees east with a magnitude of 35 pounds. So since this is fortunately a special right triangle, it's quite easy for me to find the side lengths. Using my special right triangle ratios, I get 35 root 2 over 2i plus 35 root 2 over 2j. Now, as a decimal, that comes out to be about 24.75i plus 24.75j. force 2 acts south 30 degrees east. So again, knowing it's a 30, 60, 90 triangle, and the force being exerted is 55 pounds, using my special right triangle ratios, I can see that the I component is 55 over 2I, and the J component is 55 root 3 over 2J, just using my special right triangles. And so those decimals are 27.5I, negative 47.63J. Now, to get the resulting force, which I call normally F of R, but you could just say that you're adding them because that's really what it is. You just add the two vectors together. So you use the decimals. So I'm going to add the 24.75 and the 27.5, and I get 52.25I. Add the two J components together, so it's going to be a resulting negative 22.58J. So that's the result of the forces. Now to find its magnitude, I just use Pythagorean theorem on this vector here. So you would do the square root of the 52.25 squared plus, it is negative, but since you're going to square it, it doesn't really matter. So you do a squared plus b squared equals c squared, which gets me just about 56.92. This would be in force, so it's newtons or pounds of force. The last part is the direction. So once you have the resulting vector, as stated previously, if I do tan inverse, I could do J over I, 2,5, there we go. And I end up with the angle negative 23.65 degrees. Now, you should be pretty comfortable in adding 360 to this to get a positive angle, right? If it's a negative angle, just add 360, it's the same direction. The only thing I want to point out, though, is if you're a fan of submitting your answer in bearing form, which is what the question is giving to us, what you want to think about directionally is I kind of sketched out where 336 would be roughly. Remember, bearing is always from my y-axis. So basically it passed through the 720 degree threshold. The question is, how many more degrees did I travel? So if I do this angle, the 336.35 minus 270, I get 66.35 degrees. So that's actually the bearing that I'd have to turn from south, and you can see to the east. So unless I specify I want a bearing answer, any of these answers would be fine. Okay, so they're all the correct angles. They're all just different ways of describing it. This first one is the negative from the standard. This one is positive from the standard. This one is bearing from the negative axis, okay? So these are all kind of like the same question. 5 in particular is the same exact question. The only difference is instead of using the special right triangles, you have to draw your triangles and use the 40 degree. Now remember what I said in an earlier question, since this is in bearing, if you choose to do the angle that's in the bearing, so 40 degrees, because it's the bearing angle, you're not going to do magnitude of force 1 times cosine theta for I. Because it's bearing, you would do sine theta for I. And since you might use the 40 degree, you're not going to do sine for J, you would do the cosine angle for J. Okay, if you look at my answer key, you'll see that I did swap them because I stayed in the bearing. If you switch this to its standard angle form, which would be its complementary angle 50 degrees, then you can use standard sine and cosine. Just be aware of that because it's really annoying that we always describe it in terms of sines and cosines, and for bearings particularly because the axes change, the trig functions change, it's kind of an important idea, right? The direction is relevant to the triangle. So draw it out, sketch it out, but those are your two options for these types of questions. All right, I hope that was helpful, and let me know if you have any questions. See ya.